So far, we have been looking at constructional details of typical power generators. But how does the generator actually produce electricity? Now, I'm sure you'll all remember going through this subject in study of basic electricity, perhaps several years ago. But do you still remember, say, the difference between single-phase and three-phase power, or the significance of increasing or decreasing excitation, and what is meant by reactive power? We feel that it will be worth our while at this point to review generation fundamentals, so as to lay the foundation for our discussion on generator control. This simple AC generator consists of a coil or rotor rotating in a magnetic field. The magnet has north and south poles, and its magnetic flux passes through the rotor. By convention, the lines of force or flux leave from the North Pole, pass through the rotor, and then return to the South Pole. So the lines of force at the South Pole are set up in the opposite direction to those at the North Pole. In this diagram, as we start rotation of the coil, one side passes close to the North Pole and one side close to the South Pole. The coil sides cut the magnetic lines of force, and in doing so create a voltage in the coil. This is the well-known principle of electromagnetic induction. When a conductor cuts a magnetic field, a voltage is induced in that conductor. At 0 degrees, the coil is not cutting any magnetic flux at all, and therefore the induced voltage is 0. The value of induced voltage is maximum when the coil is in the 90-degree position, because here we have the maximum rate of cutting magnetic lines of force. The direction of induced voltage in the blue conductor is opposite to the voltage in the red conductor. The voltmeter therefore receives the sum of the two voltages. As the rotor moved from 0 degrees to 90 degrees, the voltage has increased like this. And then, as the rotor moves from 90 to 180 degrees, it decreases like this. As the coil continues rotation past this 180-degree position, the conductors are cutting flux from a different pole. The red conductor is now in front of the North Pole, and the blue conductor is in front of the South Pole. So the voltage generated is now in the opposite, that is, negative direction. So we can see that one revolution of the coil produces one cycle of alternating voltage. It is alternating because one half of the cycle is in the positive direction, and the other half is negative. We have been moving the coil with the magnet in a fixed location. This is basically what's done in the brushless exciter, which provides the excitation voltage or rotor voltage for some AC generators. This will be discussed in segment E of this tape. However, this is not a practical arrangement for large AC generators, as huge slip rings would be required to take the large AC generator output current from the rotor. We could, however, rotate the magnet and hold the coil fixed to produce an AC voltage. This is what is done in most AC generators. One of the principal tasks in designing an AC generator or alternator is to construct a combination of magnetic fields and coil configurations that produce a true sine wave at the generator terminals. If we connect this circuit through a resistance and an ammeter, we find that the current follows the same pattern as the voltage. The positive and negative half cycles mean that the current is flowing in one direction for half the cycle, and then in the opposite direction for the other half cycle. As the magnet continues to rotate, it produces further cycles of voltage and current like this. These curves are known as sine waves, and values can be calculated from trigonometric tables. This, then, is how AC voltage and current are generated. You can see that for each revolution of the magnet we have one cycle. So if the rotor is spinning at, say, 60 revolutions per second, then we will generate 60 cycles per second. You recognize this, of course, as frequency, usually stated as 60 hertz. 60 revolutions per second is equal to 3,600 revolutions per minute. And I am sure we are all familiar with that number. By contrast, a two-pole machine on a 50 hertz system, as used in Europe, needs to run at 3,000 RPM. On some generators, the rotor is built with 4 poles instead of 2. That is, 2 north poles and 2 south, like this. Now, each single revolution of the rotor will generate 2 complete voltage cycles. So at what speed will the generator need to run in order to produce a frequency of 60 hertz? This can easily be calculated from the standard expression that says frequency equals P, that is the number of poles, over 2, times N, that is revolutions per minute, over 60. In this case, 4 over 2 times N over 60 equals 60 hertz. Therefore, N equals 1,800. The 4-pole machine must run at 1,800 RPM to produce 60 hertz. You can see that the required speed of the generator depends upon the frequency and the number of poles on the rotor. In practice, instead of a rotating permanent magnet, the magnetic field is provided by an electromagnet. The rotor winding actually forms a large coil, and this is fed with DC to create the north and south poles. The DC field current is known as excitation. Increasing the value of DC current increases the strength of the magnetic field up to certain limits, and vice versa. Now let's look at various ways of connecting stator windings. In this basic arrangement, the 2 ends of one stator winding are brought to the generator terminals and then connected to feed a single-phase load. In order to generate a second voltage, we can use an additional stator winding, which is placed at an angle of 120 degrees from the first winding. An AC voltage will also be generated in this winding, and it too can be connected to feed a single-phase load. But note its generation cycle, that is, minimum and maximum, occur at a different time period. In fact, the cycle of phase 2 is 120 degrees behind phase 1. That is a time lag of 5.5 milliseconds on a 60 hertz system. In a similar fashion, we can utilize a third stator winding, which is placed yet another 120 degrees, that is 240 degrees from phase 1. This too can be connected to feed an individual single-phase load. And once again, its generation cycle is 240 degrees out of phase with phase number 1. So what we have in effect here are 3 independent windings supplying 3 independent loads, but each using a common iron core and rotating magnetic field. Almost 3 generators in one. But there is a further advantage. By connecting one end of each stator winding to a common neutral point, we can provide one single return conductor for the circulation of current from all 3 phases. As the currents in these 3 phases are out of phase, the positive and negative flows in the neutral occur at different times, and therefore have a tendency to cancel each other out. In fact, if the load on each phase is identical, that is a balanced load, we find that the return current in the neutral completely cancels out to 0. Therefore, we can eliminate the neutral. We now have the conventional 3-phase system as you know it. The 3 outgoing terminals from the generator are connected by 3 lines to the 3-phase load, that is, the bus or power transformer. This in turn feeds the 3-phase power system. Most of the heavy loads on the system are actually 3-phase balanced loads. for example, electric motors. Moreover, single-phase loads, such as residential loads, are connected to the distribution system in such a way as to provide an approximate balance. The common connection of the stator winding, usually known as the neutral point, is often connected to ground. However, there are several other ways of connecting generator windings, but this is certainly beyond the scope of this program. If you'd like to know more about this subject, please refer to our other video programs. So let us now turn our attention to synchronizing. When the generator is switched into the power system, it is not sufficient to just close the circuit breaker. Certain definite conditions must be set up before the generator can be synchronized to the system. The first thing is that the generator must be running at its rated speed. This is done by adjusting the governor set point. Second, the generator terminal voltage must be adjusted to equal that of the bus to which it is being synchronized. This is done by adjusting the excitation. As the strength of the magnetic field is increased or decreased, so will the terminal voltage rise or fall. The third, very important factor is that the incoming generator voltage must be in phase with the bus voltage. What do we mean by this? Well, look at this example showing one phase only. Here is the sine wave representing the bus voltage, and here, superimposed, is the incoming generator voltage. You can see that the generator is over 90 degrees out of phase. If we closed the breaker in this condition, the generator would attempt to pull itself into phase. This could twist the windings and the stator core and create considerable damage. Of course, the great surge of power would be detected and the breaker immediately opened by protection devices. In order to provide the correct conditions for synchronization, we need to very gently adjust the speed of the incoming generator so as to bring it into phase with the bus. At the moment that the two are in phase, the breaker should be closed, and the unit will then lock into synchronism with the power system. On most modern units, this synchronization is performed automatically. However, you may find the need to do this manually on certain occasions. For this purpose, a synchroscope is provided. This is connected to either side of the breaker and, in fact, indicates the difference in phase between the two sides. For example, this condition shows that the generator is 90 degrees out of phase with the bus. As the pointer is stationary, it also indicates that the speed, that is, the frequency of both the system and the incoming generator, are identical. More often than not, you will see the pointer slowly rotating like this, indicating a slight variation in speed. In this case shown, the incoming generator is running slightly faster. If the rotation is slow enough, you can manually close the circuit breaker just before the pointer reaches the midnight position. The machine will then lock itself in synchronism and start providing load. In order to further increase power output, it is necessary to add more torque to the unit. This is done by increasing the fuel input to the gas turbine. But can we not also increase power output by increasing excitation? The answer is a definite no. Increasing the excitation will only increase voltage to a certain extent and will also increase the reactive power output of the generator. We'll be talking about this later. Let's first take a break, and then we'll come back and continue our discussion with a look at generator control. For now, please switch off the tape and thoroughly review this material in